Hello, today we are going to talk about grids and some algorithm you can do using grids. In particular, I would be interested in closest pair, computing closest pair of point in linear time. So, and the closest pair algorithm is also not only it's very nice, it's also a good introduction to what grids give us and how we can use it. So let's first define the problem. Okay, so the problem is I give you a set of endpoints in the plane, and our purpose is to find the 2 points closest to each other. Here it's defined formally as set, but potentially it can be a multi-set. For the point I drew on the right, of course, the solution would be, for example, those 2 points. And we also want the distance between the 2 points. The distance between the 2 points would be denoted by classes Cp of P. Okay, so first, it's useful to think about the problem in one dimension for closest pair. So we have a set of number on the line, and we would like to decide what are the 2 closest numbers. And of course, this can easily be solved in n log n time by sorting and then scanning. In particular, there is a famous problem called uniqueness. And uniqueness asks, are all the numbers in X, P, unique, namely different. And it's not very difficult, but it requires some cleverness. It's a well-known theorem that in the comparison model, so what is the comparison model? The comparison model, essentially, you're allowed only to compare numbers. Smaller, larger, you're not allowed effectively to do any other operation. You can also subtract number and compare the subtracted number, something along those lines. So in the comparison model, uniqueness requires omega of n log n time. And this is a very nice result. Essentially, you first need to prove that sorting requires n log n time in this model, and then you extend it to uniqueness. As I said, I'm not going to do the proof now, but if you're interested, it should be easy enough to find it on the internet. Okay, so that immediately implies that even on the line, solving the problem requires n log n time. Instead, we are going to show a faster algorithm that runs in of an expected time. For closest pair, we are going to do it in the plane, but the algorithm extends naturally to any algorithm in any dimensions, and it's a simplification of an algorithm, of a famous algorithm of Rabin. In this paper, Rabin showed 2 algorithms. One of them was primality testing, famously so, and the other one was this how to compute closed pair in linear time. And of course, to get this linear time, you have to break the above lower bound. So we're going to allow to use 2 things: randomness. Randomness means that we allow the algorithm allowed to make random choices. The right way to think about it is that you can ask the computer to give you a random number, an integer number between 1 and n, or a random bit and so on, and it takes constant time. And the second thing is that we're going to use the flow function. Now, the flow function is something that people theoreticians don't really like, because you can get into horrible mess if you allow the flow function in the RAM model, because you can pack numbers into a lot of numbers into a single number and then do essentially vector calculation quickly. This is not going to be something that our algorithm really do, and in practice flow function is fine. So we're just going to assume that given a real number x, we can compute its flow, or if you want, its ceiling in constant time. And this is, of course, completely realistic, because any modern CPU would have an assembly command that does that. So that's all good. Okay. So what is about grids? So of course, it's a bit silly to talk about grids when there is a perfectly usable grid on the screen. So let's use it. So a grid is just a partition of the plane into tiling by squares, where usually we take the origin to be one of the vertices of the square, and then we have a side length for the side length of the square, S, of course, both in the X and in the Y. We were going to use uniform grids. The standard grid would be of length 1, but we're interested in length S. And the question, of course, is, okay, so I have a grid cell, this grid cell, and I need to somehow identify the grid cell, right? I need to give it a number. So a natural thing to do would be to identify the grid with its bottom left corner, okay? So in particular, to this end, we are going to define the following mapping. And we will call it the ID of a point, xy, the point xy. We are going to map it to the point x over s and y over s. Okay, flow function on both coordinates. So this is now, we mapped a real point into an integer point, right? So this is now an integer point. And the important thing about integer points is that unlike floating points or real points, we can use hashing, right? So we can use hashing. And here I'm going to assume that every hashing operation can be performed in constant time. Hashing is its own Pandora box, so we will keep it closed. In practice, it's quite a reasonable assumption. Nowadays, if you program in any slightly high-level programming language, hashing is done automatically all the time. It does have some minor performance hit compared to using arrays, but usually we don't care. And so that's not going to be a major thing. Okay, so why does it matter? It means that if I give you a set of points now, I can store them. If I have a set of points in the plane, I can now store them in the grid. Store. Store the point set in the grid. The points of P in the grid. What does it really mean? It means that I take for all the points of P, for every P in P, I essentially store, if you want, in a hash table, I store the point ID of P. I store the point P, right? Now you have to be a bit more careful and really store a list of points of P falling into the same grid cell. Into the same grid cell. Okay. So of course this looked like a very natural way of storing a point set. But the question, of course, is why is this useful, right? So there are two things about grid cells that are going to be very useful for us. The first observation is that if I have a grid cell, and again I identify it by the bottom left corner, so let's say that this is ij, right? Then I can immediately access the neighboring cells, right? So for example, or in fact, any cell in the area, for example, this cell here, well, its ID is going to just be simply I minus 1, j minus 1, and I can immediately look it up from the hash table and see if there is any point inside the grid cell. So throwing the point into the hash, into the grid, and using hashing, I can immediately do this lookup in the hash, find if the grid cell is empty or not, and if it's not empty, get a list of all the points stored in it. So that's already very useful. The second thing is that we can use the fact that we have a verification. We can use the parking property of the plane to perform verification. So what do I mean by that? Let's assume that verify closest pair distance. Okay, so assume that somebody gave us a distance L and claimed that this is the closest pair distance of P. Okay, and all we want to do is to verify whether it is correct or not, right? So the most natural thing to do is we're going to use a grid with side length L, right? By the way, the natural grid of side length, we're going to write it as G subscript L. This is grid with side length L. Grid with side length L. Okay. And the first observation we need is that no grid cell can have a lot of points in it, right? So specifically, a square, if a square of side length L okay, so if we give you a square and it has side length L and it has more than 4 points of P, of course this is important, then the closest pair distance of P is smaller than L. Namely, L is not the closest pair distance. The closest pair distance is smaller. And the proof of that, of course, is pretty immediate, right? Let's imagine that indeed our grid is of side L, right? And observe that in a square like that, the most point you can put that are of distance L from each other are in fact the corners of the grid cell. So the most you can do is 4. And if you need to kind of look at it a bit to convince yourself that this is the most you can do. By the way, our grid, the cells are semi-open, right? So the bottom edges are included and top edges are not included. So in fact, even 4 is not possible, but let us not worry about it, okay? because that's really not critical. It's a constant. It will not play an important case in our. It's not an important factor in our algorithm. Okay, so that's really good news, right? Because it says, first, if we want to verify whether the closest pair distance is equal to L, draw all the points of P into a grid, right? Stream P into draw P into G of L. And of course, if you have a hash table, you can easily, for example, scan all the values stored in it, which would be all the grid cells that are not empty, containing the points of L. So you scan them and you verify all cells contain at most 4 points. If any of them contain more than 4 points, you immediately say no, thank you. The closed pair distance is smaller than L. So that's easy. In fact, really what you should be doing is you should be doing the following for every grid cell in G of L such that P contains some points, that the cell contains some point of the grid, right? You should just do compute, right? So after the first check, what you should do, you should go over all the grid cells again, for example, and you compute by brute force the closest pair distance of the points inside the grid cell. Of course, the naive algorithm just go over all possible pairs, but since this set size is at most 4, this take constant time per grid cell. And there are n grid cells, so this would take constant time. Okay. And if any of those distances is smaller than L, we can immediately say no, thank you again, I guess, if we want to be polite, or just no. But this is not quite enough. Why it's not enough? Because, of course, what can happen is that there are 2 points that are in different grid cells, but they are very close together, like in this case, right? And that, of course, is bad, right? We want to discover this. So what we're going to do, we are going to, for every such grid cell that is not empty, not empty, not empty. So now we are going to do something interesting. We're going to look on all the points in the cluster of P, cluster of the cell, and P. Let's call this Q of the cell, just for so you have something. So what is the cluster? So for a grid cell in 2 dimensions, its cluster is all the grid cells that touch it, including itself. Of course, the fact that the grid cell touches itself is against the Jewish-Christian set of beliefs, but let's not go into that. So in this case, for example, the cluster is just going to be, and in fact, in any grid in the plane, it's going to be 9 cells. In higher dimension, it's going to be 3 to the d, right? So it's a constant, right? We are considering d to be a constant, so this is a constant. So we go over all the grid cells, and for each one of them, we extract the points stored in them, right? To remind you, in every grid cell now there are at most 4 points. So this overall is going to be Q of the cell. This is going to be at most 36 points. Q of the cell is going to contain at most 36 points. Okay? Okay, so 36 points, and now we're computing again the closest pair of Q. Maybe I should use the blue color. We compute the closest pair of Q of the square, right? So this again, since the number of points is a constant, this is going to be constant time, right? And we do it for every grid cell that is not empty. So overall, this is going to take linear time, right? And again, we check the closest pair distance we computed. We check if it's smaller than L. If it's smaller than N, we say niet. If it's equal to L, we say yes, this is the distance. Observe that we will discover it, because if the closest pair distance is exactly L, then the 2 points realizing it are going to be in one of the clusters we are checking, right? So, and if it's larger than L, we will say, well, it's larger, because the value we compute is larger than L. Notice, of course, that if the closest pair distance is much bigger than L, then our algorithm would not find it, right? It would only encounter a singleton in all those clusters, and then it would just say, well, we don't know what it is, but it's definitely much bigger than L, right? So what we got is the following result. Lemma given P, set of endpoints in the plane, we can, in linear time, of n time, in of n time, we can decide if Cp of P is equal to L, bigger than L, or smaller than L, right? And one very nice property of this verification algorithm is that if the closest pair distance of P is equal to L, in fact, we are going to have the 2 points realizing it. We computed the pair realizing it. The closest pair. The closest pair. Okay, so that's good. Now, the next idea, and this is kind of a very common idea, so it's good to get familiar and comfortable with it. We're going to do the following. Let's take the points P and order it. In our case, we're going to order it in a random permutation. Okay, so it's not obvious first time you hear about random permutation. Order points in random permutation. Okay, so the easiest way to do this is, for example, you have the array of the endpoints. You randomly pick an index between 1 and n. The element that you picked in the array, you output it, and you delete it from the array by moving the last element in the array to this location, right? And decreasing the array size by 1. So if you do this, in linear time, you compute a random permutation, and it's uniform. So that's going to take off n time, right? So computing a random permutation, we can do it for free, essentially. Okay, so we have a random permutation. But for the time being, let's not think about it as random, because that would kick in only in the kind of the last step. And now what do we want to do? Well, we want to look on Li. What is going to be Li? It's going to be the closest pair distance of Pi, where Pi is the first I point. Right? Pi, capital Pi, is P1 all the way to Pi. Right? So this is the closest pair distance. And okay, so Li is the closest pair distance of Pi, and implicitly, I'm also stating that not only I know the distance, I also know the 2 points realizing it. And let's think about maintaining the grid of size Li, where I store, inside it, I'm going to store the points of Pi, right? And now Pi plus 1 comes along and wants to also be included, right? So this is called an incremental algorithm, right? We're inserting the points one after another, and we are trying to maintain the quantity that we care about, which is the closest pair of distance of the point inserted so far, namely Li in this case, or Li plus 1. Now, there are two possibilities, so let's kind of go through them. One option is that Pi plus 1 is lonely, it's in its own grid cell, on its own. In that case, there is no problem, right? Because I can find the grid cell in the hash table in constant time. I figure out there are no points around it. I can also, in fact, look on the clusters. And let's assume that is also empty. And if this happens, I know that the closest point to Pi plus 1, it's going to be pretty far away, right? It's going to be further than the grid length distance, which is Li. So in this case, Pi plus 1 is isolated. And in particular, we have that Li plus 1, the closest pair of Pi plus 1, is the same as Li. Nothing changed, right? And the nice thing is that this takes us constant time, right? We just inserted something into the hash table and we are happy, right? So this is if things are lucky. But let's assume that we are not lucky, right? What could be a bad situation? Well, to begin with, there might be a point inside the cluster which the distance is still bigger than Li plus 1, right? Still bigger than Li. So the closest pair distance doesn't change, but it almost changes. But if you think about it, this doesn't really matter, right? Again, all we need to do is insert Pi plus 1, see that check in its cluster for its nearest neighbor. If this distance is bigger than Li, then we set Li plus 1 to the Li and we move on. And that takes constant time. So the bad case is when you insert Pi plus 1 and tragically and sadly, there is a point nearby, right? So maybe this is Pi plus 1 and this is P17. It's always P17 that makes the trouble. Okay, so Pi plus 1 and P17, and this distance now is bigger. This distance is, smaller, not bigger, of course. This distance is smaller than Li, right? So first I can compute it, right? Because again, since the cluster side length was Li, we already argued that this cluster had at most 36 points, so we can extract all the points of the cluster in constant time, and we can compute the closest point to Pi plus 1 by just scanning all the other points. That takes constant time. So in constant time, I can update the closest point to Pi plus 1. Great. Okay, so I updated it. Okay? So that's good. But now that I updated it, so in fact, what happened is that in constant time, I computed Li plus 1. This distance that is smaller than Li must be the new smallest distance, right? Because it must involve Pi plus 1, and this point is the closest point to Pi plus 1. So we computed Li plus 1, but the problem is that the grid is now not updated, right? It's the wrong size. That's bad, right? So if this happened, we are very sad. It's important to be sad when the occasion calls for it. And what we do, sad if Li plus 1 is smaller than Li. And then we recompute what do we do? We recompute the grid, right? But now we are computing it in the new size, Li plus 1, on the size Pi plus 1, right? So I take the points, all the first I plus 1 points, reinsert them into this new grid. That's going to be expensive. That's going to take off I time. Very sad. Okay? So naively, what's the running time? But the nice thing is at the end of this algorithm, we inserted the point Pn, and we got the closest pair distance. So this algorithm works, right? But the worst case running time is what? Is off, well, there are end steps. In each step we spend linear time maybe rebuilding the grid. So this is off n square. This is very bad. Okay, so let's see if we can do a better analysis. Right. And to do a better analysis, we have to use the fact that this permutation is random. Right. So I'm going to define a random variable, which is called an indicator variable, which is 1 if and only if Li is smaller than Li minus 1. Namely, the closest pair distance changed when I inserted the ith point. And the question, of course, is what's the probability of xi to be 1? Right? And what we're going to do, we're going to do a very nifty analysis, which is called backward analysis. Right? So backward analysis says, okay, let's assume that I've chosen the first I point in the permutation, but I don't know who they are, right? I just chose them and I insert them, right? Namely, I have the first I point inserted, but they're unlabeled, right? This is, I'm after the ith step of the algorithm was executed. There is a closest pair, of course, which I'm going to mark here. This is the closest pair, and this is Li. Let's assume that the closest pair is unique. If it's not unique, it turns out that this probability is even smaller. So this is, let's just assume it's unique. So there is a single specific point that realize the closest pair distance. And the key observation is that the closest pair was changed if and only if the last point, the ith point, was one of those 2 points, right? So we have I elements. We have random permutation of them. And there are 2 special elements, right? And the question is, what's the probability that the special element, that one of the special element is last? Here last mean in the random permutation, in a random permutation of the I elements, Okay, now of course every element have equal probability of being last, 1 over I. Since there are two special elements I'm looking at, the probabilities as such twice this, so this probability is 2 over I. Right. So let's go back to our stuff. Okay. The probability that we have to rebuild it, the probability of xi equal 1 is 2 over I. Okay, this probability is 2 over I. This is the probability that in the ith step I have to rebuild the grid, right? Now let's start with a naive bound. a naive analysis because it's somehow useful to recall things. So the number of times I have to rebuild the grid is sum of xi going from 1 to n. And I'm looking on the expected number. So this is number of times. This is number expected number of grid rebuilds. Yes, right. Every time you rebuild the grid, you make it great again, or grid again, I guess. And now we're going to use linearity of expectation. Linearity of expectation just means the expectation of some variables is the sum of the expectation. If you want, expectation is a linear operator, right? And now xi, I told you that it's 1 if the event happened, namely that the closest pair distance changes. If it doesn't happen, it's 0, right? It's an indicator variable. And it's a standard observation that the expectation of an indicator variable is equal to it's equal to what? Well, it's equal to 0 times whatever, because we don't care, and 1 times the probability that xi is equal 1, right? Namely, this is equal to the probability of xi equal 1, right? So this is the reason why people like indicator variables. They lead very quickly to probability. So this is the sum I going from 1 to n of probability of xi equal 1. This is by what we just computed at most I going from 1 to n 2 over I. And this is the harmonic sum, and everybody knows that's how it goes, that this is off log n. In fact, it's 2 log n plus some constant, but whatever, it's off log n, right? So this says that with high probability, in expectation, the grid is going to be rebuilt log n time. Now, by the way, let me comment that this is also true with high probability. The number of rebuilds of the grid throughout the algorithm execution is going to be off log n, both in expectation and with high probability. High probability means that the probability that it doesn't happen is polynomially small. Something like, if you want, 1 over n to the 10th, right? This is the probability of this not happening, the bad probability, right? So this is what we call with high probability. The formal definition of high probability is somewhat different. Let's not go into that here. Okay, so we are already in pretty good shape because if we are doing every step of the insertion take constant time unless we do a rebuild, but we are doing an expectation only log n rebuilds. Every rebuild takes log n time, so we immediately get expected running time. Expected running time is of n log n, right? Well, it's of n log n plus n, which is of n log n. Okay, this is not very interesting. Well, it's still interesting because it's still simpler than other algorithms that achieve n log n time for the closest pair, but we are not here for this, n log n time algorithm. We really want linear. So what would be the trick? The trick, we are going to use the fact that the rebuilds are really not off each rebuild. The early rebuilds cost much less, right? So our analysis was very pessimistic, and it was so pessimistic that it was wrong. So let Ri be the running time in the ith iteration. And we observe, what do we observe? Well, what is Ri? Well, Ri is it's always off 1, right? Because we need to do some stuff. And then if things are bad and we have to do a rebuild, right? If xi is equal to 1, we have to do a rebuild and then we have to pay I, right? So we get this. If you want, let's write it more. Let me ignore the O just to keep things simple. So it's 1 plus xi times I, right? Okay. And now, as such, what is the expectation of Ri? This is the expected amount of time the ith step of the algorithm takes. Well, it's the expectation of 1 plus xi times I, right? Okay, it's as I mentioned, expectation is a linear operator, and I, for our purposes here, I is fixed, so it's a number, so we can take it out. So this is 1 plus I times the expectation of xi. Well, expectation of xi, we already argued that this was at most 2 over I. By the way, at most 2 over I for the case where the closest pair distance is realized by more than one pair, and then this distance, in fact, this expectation can be 0, right? So it's at most 2 over I. So this is at most 1 plus I times 2 over I. Happily for us, I cancels out, so we get this as 3. And of course, we were ignoring the O, so really that what it means, that expectation of Ri is O of 1. Namely, the expected running time in every step of the algorithm is a constant. And what is the expected overall running time? Expected runtime of algorithm? Well, it's the expectation of the sum of the Ri, I going from 1 to n. We use linearity of expectation because literally this is the only trick we know. And that's all the trick that we need, right? Each one of them is n, so this is I going from 1 to, this is to sum from 1 to n of O of 1, and this is of course O of n, right? And we are done. So theorem the running time for a set P okay, so we got the following result. Given a set of P of n points in the plane, but in fact this works, as I said, for any point set in Rd, where D is a constant, one can compute the closest pair of points and the closest pair distance in expected linear time. Notice that the constant here in the O is pretty bad. It's something like 2 to the D. It's exponential in the dimension. This would be true more or less for all the algorithms we see in class, unless explicitly stated. Otherwise, we will do in a lot of cases. So this is kind of pretty cool. By the way, a natural question is, can you replace the expected here with high probability? And the answer is yes. But I think it's because this algorithm, in fact, does not have linear time with high probability. And the algorithm, I think it's fair to say, is completely crazy. So that get high probability. It's from some follow-up work that I did with my student. So it's in the net and prune work. So this is kind of very nice. It gives us a feeling for what we can do with the grid. Now, one nice thing that we can do with this framework, for example, is to compute the two closest pairs. Now, one way to think about the two closest points is to look on the diametrical circle that they define, right? So the two closest points define the maybe I should just draw a bigger circle, or try to draw a bigger circle with my abilities. So really what we found the smallest circle containing 2 points, right? This is really this thing. So it's of course natural to ask the question for arbitrary k. Right? Compute the smallest disk containing k points. Now it's believed, and it would be extremely surprising if it's not true, that you cannot do better than nk. The lower bound, the believed lower bound is nk. Think about k as being larger, like square root n, right? And it's believed that you cannot really, it would be pretty amazing if one can do better, significantly better, right? Not just some noise like polylog. So the natural question is how to compute the smallest disk containing k points, approximately, right? So we are willing to find the smallest disk containing k points, and it can be up to at most twice larger than the optimal disk. It turns out that one can imitate this algorithm and do it, and it's described in the class notes. The description in the class notes, the algorithm is very nice, but it's the analysis is kind of clever, or I don't know if clever is the right word. It's kind of tedious, and it turns out that you can get a better algorithm. By better I mean simpler algorithm, by the net and prune technique, which is what we are going to discuss next. Thank you.